Okay, so 3 shapes down, just 1 more to go. This is our last conic section shape. This is a hyperbola. So the equations, again, the hyperbola itself has a very strange definition. The important part is what the graph actually ends up looking like here. So some really important features that I want you guys to look at. We still have the center. All of them still have a center, so notice these ones are centered right at the origin, and that's actually not labeled, but they all do have a center. And then we still have vertices and co-vertices. Okay, so notice your vertices go right here, and your graph actually crosses right through those vertices. Same thing right here and right here. That's a vertex, that's a vertex. And then your co-vertices aren't actually on the graph once it's plotted, but you see, and once we actually start graphing, they do make a very, very important part of our graph. So this is a co-vertex, this is a co-vertex, so is this one, so is this one. Now notice, like I said, they're not actually on these little boomerang shapes, but there's a little dotted box that we make, and knowing the co-vertices, that's very important to making this dotted box, and making the dotted box is super important to actually graphing the equation, okay? So here's all the features you're gonna see. You're gonna see a center. We're gonna plot vertex 1, vertex 2, co-vertex 1, co-vertex 2. Same thing down here. You've got the center. You have the vertices right here, co-vertices right here. And then once you have those 4 points, you're gonna make this box, this little dotted box that will guide your shape. Same thing with this one. Once you have the box, you will draw these lines in. These lines are asymptotes. We've seen asymptotes before, but these ones are diagonal asymptotes. That's new. So you draw these diagonal asymptotes here and here, right through the corners of the box. Same thing with this one, diagonal asymptotes right through the corners of the box. And then because you have those boxes and the asymptotes, you're able to graph the hyperbola exactly the way you should. So see, like, you know exactly how wide or how narrow the hyperbola is supposed to be because you've got those asymptotes in your graph. Okay, so those are kind of the main features of a hyperbola. Now with an ellipse, I told you guys that technically there are there's a horizontal ellipse, there's a vertical ellipse, but it really doesn't technically matter. With hyperbolas, it actually does, very much so. With ellipses, they're all ovals, like, so they're skewed a little bit more in one direction. That doesn't actually matter. With hyperbolas, you do, because sometimes the 2 pieces go left and right, other times the 2 pieces go up and down. So it is actually super, super important to note that this one is the horizontal one, and then this one right here is the vertical one. So with hyperbolas, definitely a difference in terms of which one is which. Okay, so let's start to look at our general setup and then some examples. So here's our setup. I'm gonna start you guys off with a slightly easier one. Here again, x and y are by itself. So I want you to notice something about the equation. It's almost identical to the equation for an ellipse, except that this is subtraction. Okay, subtraction, subtraction. So now it's really important that we have 2 different equations because subtraction, the order does matter. So for both of these, the center is just right at the origin, just 0, 0. And that's because the x and y are by themselves. We'll get into the h and k eventually, but I'm going to start you guys off with just simpler hyperbolas that are centered at the origin. The orientation, that tells you which way it's going to face. Okay, so this one, because the x is first, and x moves left and right, this is going to be a horizontal hyperbola. Okay, so x first means it's horizontal. Y, remember, is vertical. That tells you how far you go up and down. So that makes this one a vertical hyperbola. Okay, our transverse axis, that's like our main axis. That connects the vertices. So with this one, our main axis goes to the left and to the right. And I'm going left and right A units. So if I go to the left A and to the right A, then I end up with 2 A units. Same thing here. My transverse axis is kind of the main one, but for the main axis, I'm going up and down. So I'm going up A units, down A units, grand total of 2A. And then the exact opposite for the conjugate axis. Conjugate axis is kind of like the other axis. It doesn't actually touch the graph, but it helps us make that box that I was talking about. So the conjugate axis, the opposite, the other axis, goes up and down for this one. And we're going up and down B units. And then this one, the opposite axis goes left and right. So left B, right B, that ends up being 2B units. And the vertices, for the horizontal, our vertices go left and right. So we're starting at 0, 0. We go to the left A units and to the right A units, and then we don't go up or down. So is the vertices. Here, this one's vertical, so we go up A units, down A units, we don't go left and right, we just go up and down a units. So those are the vertices. And the exact opposite with the co-vertices. My co-vertices with this one go up and down. So I don't go left and right, but I go up or down b units. And then here, I go right or left b units, and then I don't go up and down. Okay, so those should help you while we're coming up with equations. So these first two examples, example 1 and example 2, we're going to create the equation. And so knowing some of the different features right here will be very helpful. So I'll continue to flip back and forth while I'm doing these examples. So vertices at 0, 2 and 0, -2. So that must make it one of these. So if our vertices are 0 and then a number, it must make it one of these. And so it must be a vertical hyperbola. So that makes this value right here a. So that means that a is 2 according to this. And then co-vertices at plus and minus 4, 0. So that's this right here. Again, vertical. So this means that b is 4. And then we know that this must be a vertical hyperbola. Again, just because my vertices go up and down and my co-vertices go left and right. That makes it vertical. So vertical, I have y squared over, and then the number of units up and down is 2. 2 squared is 4. Minus, and again, since it's vertical, the x squared goes second, over how many units left and right? 4. 4 squared is 16, and then we always have equal 1. So that's our equation that we use for that one. We're going to do something really, really similar with example 2. So let's take a look here. We've got vertices at -5, 0, and 5, 0. So that's plus and minus 5 for the vertices. So for the vertices, that's this form right here. So it must be a horizontal hyperbola. So that makes this a. A is 5. And then this is a little tricky. So conjugate axis of length 14. So the length of the conjugate axis is 2 times b. So if twice ends up being 14, that means that b must be 7. Okay, so we know that 2b has got to be 14. So that means that b must be 7. Okay, and then last little detail, I know that it is a horizontal hyperbola. The reason I know that is because my vertices go left and right. If my vertices go left and right, it must be horizontal. So horizontal starts with an x squared over 5 squared, which is 25, and then minus, the y squared goes next when it's horizontal, over 7 squared, which is 49, and then we always have this equals 1 no matter what.